All right, so like I said yesterday, I had you guys do this on your own, so let's take a look at it. So it says when there are two or more of the same root, this is known as multiplicity. So if you remember yesterday, we found some answers. I think we had like a power of 5 function, but we only found 2 roots, right? But one of the roots was like a power of, it came from a power of 3, so we said that it had multiplicity 3. In other words, there were 3 zeros essentially that were happening there. And then the other one had like a -3 as an answer, but the power was a 2, so we said it had multiplicity 2. When you added the multiplicities, even though it was a degree 5 power, when you added the multiplicities of a 3 and a 2, it came out to 5. So it actually equaled to the right amount of answers, even though we only found 2 roots, right? We only found 2 of them. So that's what they're talking about over here. It says when there are 2 or more of the same root, this is known as multiplicity. So we'll just kind of highlight that whole thing for you guys, because that is a definition. Okay, it says the function of above has a root multiplicity 3 at 0, 0, and a root multiplicity of 2 at -3, 0. We did that. It says a root of multiplicity 1 is usually called a simple root. So that might be really good for you guys to kind of mark down too, right? We call it a simple root if it has multiplicity 1. In other words, if it's just like parenthesis x plus 2. The power on the outside is a 1, so we don't write it, right? Or if it just has like x only, right? No x squared, no x cubed, nothing like that, just x. So we call those simple roots because the power is a 1. But once the power becomes a 2, 3, 4, 5, 6, 7, 8, etc., those are called multiplicities, okay? So the question I had you guys do, it says, what are the roots of the following? Y equals to x plus 1 and x minus 2 to the 4th. So let's go ahead and solve that. We'll kind of do it a little bit on the side so we can list it. But first off, I'm going to get the first thing that they list, x plus 1, and I'm going to set it equal to 0. Okay? And when I do that, I'll solve by subtracting what? 1, I get -1. So one of the roots is x equal to -1. What is the multiplicity on that one? Notice I just solved it right here. What's the power on that parenthesis? A 1. So then we call it a simple root, which means it has no multiplicity. Okay? Now we're going to solve x minus 2 to the 4th equals 0. And since the power is a 4, I need to take a 4th root of both sides. Okay, so I'm going to take a 4th root of both sides. So that's going to give me x minus 2 equals 0. So if I add 2, I get x equal to 2. So my other answer is x equal to 2. What's the multiplicity on it? 4. So I'm going to write mult of 4. Okay, that way you don't have to write multiplicity over and over again. But multiplicity of 4. So that means one of the answers is -1. That's one root. And then the answer of 2 comes out how many more times? 4, right? So 1, 2, 3, 4. So that's a power of 5. Okay? If you're ever trying to figure out your degree, when they ask you like what's the degree of this function, just add this number there and that number there, and that means that this must be a 5th degree function. Okay? So it must be a 5th degree function. All right, so for the next part, it just says describe it. So we're going to say y has a simple root of x equal to -1 and a root of x equal to 2 with multiplicity of 4. They just want you to use the right wording. Okay, if you don't call it a simple root, you're not going to get it wrong. But they just want you to know, like, this is what it's called. A simple root only occurs once. Anything that occurs more than once, we say it has multiplicity. Okay? Because it occurs multiple times. That's why they call it multiplicity. Okay? So y has a simple root of x equal to -1 and a root of x equal to 2 with multiplicity of 4. So there's a total of 5 answers. -1 happens once, and 2 happens 4 different times. Okay? So, all right, let's look at question 8. It says, based upon the degree, this is called a more disturbing example. Okay, so they're saying, like, check this one out. This is a little weird too. It said, based on the degree, how many roots would you expect to have? 3, right? So 3 roots. Okay, why? Well, that's the highest power, right? We get the highest power of 3, therefore it's degree 3. And if you remember, they said that the degree is equal to the number of roots is equal to the number of factors, right? So it should have 3 roots. Okay? Then they say factor this. Use the zero product property to solve. So I'm going to factor it for us really quick. I'm going to take out from this function right here, I'm going to take out an x, so it becomes x squared minus 4x plus 5. And then I'm going to try to factor x squared minus 4x plus 5, but what's going to happen is it's not going to be possible. Okay? I will not be able to factor x squared minus 4x plus 5 using the x method or any other method besides solving for it using the quadratic formula, but we'll talk about that in a bit. I can't factor this, okay? So let's see what it says. It says factor it and use the zero product property to solve for the roots. How many roots does this polynomial have? Well, I know that because of this is 1 root. 1 root there. I can't factor this. Okay? But I could solve for it if I use the quadratic formula. Okay? And they actually tell us to do that in number 10. So right now, you might say this has 2 roots total, right? I'm going to put 1 root, but with the question mark. Because since I couldn't factor it, if I set it equal to 0, I can't solve for it. Unless I use a different way of doing it. So look at question 10. It says, look at the graph of this function. So here it is. There's the picture. The graph has only 1 real root. It's right there. Okay, right at the origin. So if it only has 1 real root, what are the other answers called? Someone said it. Go ahead. Someone, I think you said it back there. No? Imaginary. Yeah, complex. How many complex answers, like, they come in like by themselves, or they always come in 2, right? Complex numbers always come in pairs. So if there's 1 real root, then how many complex do there have to be? 2. And 2 plus 1 equals 3, which is my degree, right? But they want me to solve for that in part 10. So how do we solve for it? Well, we already have it factored, so let me write it down like this. Okay, now up here, if I can, I'll solve for the easy one, the x. X equals 0, so that's one of the answers. That's why the point's right there. Okay, but I couldn't solve for the x squared minus 4x plus 5 because I couldn't factor. So the way I'm going to solve it is by using the quadratic formula. So my a term is a 1, my b term is a -4, my c term is a 5. Okay, that's from that little thing that I bracketed. Okay, so let's put that into the quadratic formula. X equals -b, that'd be a +4 plus or minus square root of b squared. -4 squared is 16 minus 4 times a times c. 4 times 1 times 5. So that's 20. Over 2 times a, so that's 2. Well, x is equal to 4 plus or minus the square root of -4 over 2. Well, what's the square root of -4? 2 what? 2i. So x is equal to 4 plus or minus 2i over 2. Now, of course, your books always want you to simplify. And on the test, they didn't make you do that, so that's nice. But in the books, they always want you to simplify. So dividing everything by 2, I get 2 plus or minus I. So notice, I had one answer here on top. And I have 2 answers there. So do my answers still add up to the degree? Yeah, one real, two imaginary, or if you want to call them complex, right? So one real, two complex, that's 3. This was a power of 3. So it says, it is a fact that complex roots always come in pairs. I'm going to highlight that again because that's something I'm telling you guys, right? That's always true. If you find one complex number, there is another one, okay? And it's just like a change in sign for your imaginary part. Give a reasonable justification why. Here's the reason why. Complex conjugates. We talked about this before. If you have A plus BI, then you must have A minus BI. Or if you have A minus BI, then you must have A plus BI. This is in your notes, by the way. If you had, remember I put if you have a positive BI, then you had a negative BI. And if you have a negative BI, you must have a positive BI. Those were called complex conjugates. This is why we always have 2. Because if you find one, then the other just has a different sign in the middle. That's all. Now, if there is no middle to it, like something like this, but you do have just the imaginary unit, then if it's positive, the negative one exists. If it's negative, then the positive one exists. Okay? Always 2. Okay? Always 2. So it says, okay, well, revising what we learned now. So initially we said that the degree on the function equals the number of real roots. And then later on we said, well, the degree of the function tells us how many real roots we have total. Maybe they're real, maybe they're imaginary. We're not sure. And then we just did this problem and they say, okay, well, now that we've seen all this other stuff happening, let's revise our statement and we create what's called the fundamental theorem of algebra. Okay? And the fundamental theorem of algebra says any polynomial function of degree n has exactly n roots, including things that repeat, including complex roots. Okay? So the number of roots has to add up to the degree, but they don't have to be like only real roots. It can be imaginary roots. It can be numbers that repeat 4 times. So let's say you got x equal to 2, but it happens 4 times, so it has multiplicity 4, right? Things like that can occur. All right? So just remember that the degree should equal to the number of answers. But the types of answers you get are not necessarily always real numbers. Okay, they might be imaginary. They might be repetitive. Okay? So let's go over here. Now, yeah, this is that next page. It says graph both of the following polynomial equations with the graphing calculator or graphing software. Sketch the graphs and include the roots. So here's where I have to pull out Desmos for you guys, okay? So x minus 1 to the third. Let's do this one here. Not Desmod. All right. By the way, I really recommend, especially if you're a junior, that you get used to using this program because on that state test, this is the calculator they let you use. Okay? Now, my youngest daughter says, yeah, but that's not a calculator. I say, yes, it is. Look, 2 plus 3 gives you 5. It does calculator stuff. Okay? But it also graphs. So some of you guys don't have graphing calculators or they're not going to let you use calculators in the test. They'll let you use this. So know that you can use this for anything. Okay? Calculating just addition, subtraction, division, multiplication, anything. Okay? So if let me see if I'm right. Hold on. I think I pressed the wrong number. Will it do it? No, it won't do it. Okay. I thought maybe it would do something else. But anyway, here's our graph, guys. They said graph this thing. Let me just show you what you need to make sure you do. Okay? You see those 2 points? On your graph that you're about to draw, make sure, just make a small graph. Make sure you include the y-intercept 0, -1 and the x-intercept 1, 0. Okay? So let me go back and I'll draw this for us here. So I'm just going to get a quick chart, just something small, and I'm going to put a mark here and a mark there, okay? And the graph goes like this and like that. So it says graph both the following polynomial equations with the graphing calculator, graphing software. Sketch the graphs and be sure to include the roots. So how many roots does this have? Remember, roots is where it crosses the x-axis. 1, right? It only has the point 1, 0. But that's only one root, right? Does it have multiplicity to it? Possibly, right? How many? What would the multiplicity be? If I only found one root, but my degree for this function is a what? A 3. Then what might be the multiplicity on that root? 3, because it has to add up. If there's only one answer, then it must add up to 3. The number of times it repeats, it must be 3, right? So, all right, we don't know for sure, but that's a good idea to think of it that way. How many roots should the next one have? It should have, well, not 2. That should have 3. Now, the 2 in the front is just a number. It's not a variable, so we don't count it. But x plus 2 squared and x minus 1 to the first, you add the powers, that tells you your degree. So 2 plus 1 would be 3. This is actually a cubic function. Let me graph this for us really quick. So 2 times x plus 2 to the second power. And then what's the other factor? X minus 1. Thank you. So we'll get rid of this picture. All right, so here we go. So how many roots do you see? 2 of them, right? Only 2. Does one of them occur more than once? I told you yesterday something about when it bounces off, right?
I would say that the 2 repeats once, but it's being blocked down.
Yeah, remember I told you when it crosses the x-axis and it gets shot back, that means it must have an even multiplicity, like a power of 2, a power of 4, a power of 6. Since there's 2 answers right there, and I have to add up to 3, that means that negative 2 must have a multiplicity of 2, and then this is a simple one, because it just goes through it, right? So 2 plus 1, that'd be 3, okay? So yeah, that would be your 3 different solutions right there. So let's go ahead and graph this really quick. Let's see, where is it at? That and that. Just a quick one, nothing amazing or anything like that. So we said negative 2 and so it's 1, 2, and the other one was at 1. So we're just gonna draw the graph like this. And just say that it has 2 different places where it crossed, there and there. Okay, so negative 2, 0, 1, 0. Now, if you wanted to find out if it had multiplicity 2, etc., then what you do is you grab this piece here and you set it equal to 0 and solve, and you grab this piece here and you set it equal to 0 and solve. And you can find out if it has multiplicity, yes or no, and stuff like that, okay? So, let's continue. It says, list all the roots from above. So, all right, the 1, 0. If we solve it, let me just show you here. If we solve it, because that's the factor, I would have to take a cubed root of both sides. So I get x minus 1 equals 0, so x has to be 1. So x equals 1, multiplicity of, look at the power that it started with, power of 3, multiplicity of 3. That's one of the roots. Let's go to the next graph, because that's all I need, right? If it's multiplicity 3, that means it matches the degree, so we're good. Okay? The next graph. let's solve for not the 2, because the 2 equal to 0 doesn't make any sense whatsoever. But x plus 2 squared equal to 0. That's one of the factors. We'll take a square root of both sides. By the way, I put a 2 there because that's what it's supposed to be, but a lot of people don't do it. That's okay if you do or don't. So x plus 2 equals 0. That means x equals negative 2. So x equals negative 2 multiplicity of what? This one's a 2 right here because it came from that 2. That power of 2. So multiplicity of 2. And then the last one had to be x equal to, well, let's see. X minus 1 equals 0. So x equals 1. So this would be a simple root. So they said, okay, 14. Look at the graph that we had up here. Okay? They say visually, what happens at a simple root? So at x equal to 1, did the graph bounce off or did it go through? It just went through. So simple root, it goes through. All right. They say what happened at a multiplicity of 2? I'm going to write even multiplicity. Okay, I'm just going to try to make it more general because it's important you guys understand it's not just 2, it's 2, 4, 6, 8, 10, 12, 14, 16, 18, etc. Okay, even multiplicity. What happened at the answer that had multiplicity of 2? So at negative 2, what did the graph do? It bounced, right? It didn't go through. It wasn't allowed to go through. It got to the point and it was rejected back to where it came from, right? So it bounces. Okay, some teachers like to say it kisses the graph. Okay, what about multiplicity of 3? So I'm just going to write odd multiplicity. So my odd multiplicity occurred on that graph. Did it bounce off or go through? It goes through. So even powers bounce. Odd powers, which includes the number 1, right? The simple roots. Odd powers go through. Even if they have multiplicity of 7, they go through the graph. If they have even multiplicity like a 4, it'll bounce off the graph. Okay? Knowing that will help you sketch graphs even though you don't know what they look like. Okay, knowing those little ideas. Any questions before I move on this? Because I think we're going to the next page after this. All right, so we're going to go past this, okay? Let's go to 15. You can put a big old line if you want through the other one if you want to. That's fine. You don't have to. But that way you don't say like, man, I forgot to write those notes. Like, no, you didn't have to. All right, so let's take a look at 15. All right. It says, sketch the function. Now, I don't know about you guys, but I don't know what this function looks like. Okay? But I have enough clues. All right? So let's see. What's the degree? Can anybody tell me the degree for that function up there? It's more than 3. 4. Because 1 here, 1 there, and 2 on the other one. So 2 plus 1 plus 1 is 4. Okay? So that was the degree 4. What are the roots? So someone said 2. How did you get 2?
It's the highest.
Well, that's the degree for this piece, but the root means the solutions, right? Someone said 2, negative 3. How'd you find that real quick? 0. Yeah, that 2 makes this 0, right? Negative 3 makes this 0. What makes this 0? Negative 1, so notice you actually don't have to do the zero product property if you just think about what makes it 0. Right? That's faster. Now, I show the work because maybe people can't do that in their head. But, yeah, if you guys can do this in your head, do that because otherwise it's kind of like a waste of time. Right? But, all right. So we found out, and I'm just going to put the work right here on the side. Okay, x minus 2 equals 0, so x equals 2. X plus 3 equals 0, so x is negative 3. And x plus 1 squared equals 0. So if you take a square root, you get this. So I'm just doing it real quick for people who maybe needed to see the work. So here are my roots. X equals 2, negative 3, and negative 1. So guess what I'm going to do? On my graph, I'm going to put a dot at 2, negative 3, and negative 1. Because they're my roots, which means that's where it crosses the x-axis. Okay? Now, just out of curiosity, will my graph go through the point negative 3, or is it going to bounce off of it? It's going to go through it. How do I know? Because, yeah, look at the power. It's a positive 1, so that means it's odd, therefore goes through. What about negative 1? Is it going to go through there, or it's going to bounce off? For negative 1, it'll bounce because the power for it would be an even, a 2, right? X plus 1 squared. What about at 2? Let's go through because it's x minus 2 to the first, okay? All right. So now that we kind of know that, all right, end behavior. Well, this is a power of 4. Now, look at the front of the equation. Is it positive or negative? So look right there. Positive, right? Since it's a power of 4, isn't it supposed to start top left and top right? Okay, that's end behavior. That's the big list you're supposed to know, but I know a lot of us use cards. But top left, top right. So here we go. I'm going to start up here. Top left. We said you have to go through negative 3. Okay? So I'm going to go through negative 3. And then I have to go through or bounce off of negative 1. Bounce off. So check it out. I got to eventually turn back. But once I hit that answer, I got to bounce. And then I got to turn back. And am I going to go through or bounce off of 2? Through it. Now, is this the right answer to this sketch? I doubt it. But is it a sketch that resembles what's supposed to happen? Yeah. Okay, right now we'll check to see how badly I did it. Maybe I'm right and I got it right. But I'm guessing I'm wrong. Okay? But let me just write end behavior top left to top right. Okay, check your sketch with a graphing calculator or graphing software. How closely does your sketch resemble the one? What might be the difference? I can tell you the differences are going to be the heights in these loops, okay? Yeah. I can tell you that the differences will be the heights in those loops. Now, let me see. Let me write down that function. So, keyboard's always easier. All right, so it's x minus 2, and there's an x plus 1. What was the other one? There was an x plus 1, an x plus 3, right? Oh, that was squared. Thank you. Yeah, that one was squared. And then an x plus 3, right? Oh, okay. I was going to make the first one longer than the other, but I mean, it's not terrible. Granted, I was supposed to go down 16 units on the second loop. And on the first loop, I was supposed to go down 5 units. Let's see what I did. I went down 3 units on the first loop and only 5.5 the second. So it's wrong. Okay? But it's a good guess. Okay? When we say sketch, that's what we mean. It's not going to be perfect, but do you get the right amount of things? Right? Do you get the x-intercepts? Do you understand? Should you go through? Should you bounce off? Where do you start? Where do you end? Right? All these things. All right. So, last thing. They wanted us to give you guys homework for this, but do you guys want me to give it to you as homework, or do you want to do it now?
No.
You guys rather do it now? All right. That's what I do. I never understand the people who are like, I'll just do it at home. It's like, why? Like, don't you just rather want to not do anything at home? That's what I'd want to do. All right, so let's sketch the graph of the following function using the information given. So we're going to kind of follow what was said on top. What's the degree of 16?
What?
2, thank you, right? X minus 2 to the first, x plus 1 to the first. So that's a power of 2. So we know it's a parabola, right? Parabolas are powers of 2. Now, what do they ask us? How many roots does, or what are the answers? What are the roots? So let's see. One of the answers will be a 2, because 2 minus 2 is 0. And then what's the other one? -1. So 2 and -1. So let me put an answer at -1, 1 at 2. Now, do 2 and -1 have multiplicities? Well, they all came from first power parenthesis, right? So they have no multiplicities. So perfect. That means I have to go through the point, not bounce off. Go through. What's my end behavior? Where do I start? Since this is a degree 2, they either both go up or both go down. Which one is it? Down. How do I know that? Because of the negative, right? So I'm going to start down here. I'm going to go through this point, through that point, and there you go. I'm done. Is my graph right? Probably not. Okay? But it's close. Okay, thank you. It's close.
Is it gonna matter if it's like if it's like too big or too small?
Well, when you're sketching, it doesn't, because you're literally, I mean, there's more I can do to this that I know I can do to this to make it way more accurate. But based on what they're having you learn, this is as good as it kind of gets. Some of you guys might have a longer loop. Some might be a little shorter. That's fine. It doesn't matter. Okay? As long as you have the x-intercepts and the way the graph kind of looks. And that's all we're looking for. All right, 17. What is the degree on 17? 4. 1, 2, 3, 4. That's correct. Okay, it's a parenthesis to the first, to the first, to the first, to the first power. So that's a 4. Okay, 1, 1, 1, 1. Now, my roots. What are my roots? -7. What else? -1. What else? 5 and 3. Okay, so I got 4 roots. Makes sense, right? So, and that's all by looking at those parentheses and solving for 0, right? So let's go to -7, -1, 5, and 3. Are all of these simple roots, or do any of these have multiplicity? No, these are all simple. That means I got to go through everything, right? Where do I start? Since this is a degree 4, they either both go up or both go down. They're both going up because in the front there is no negative. It's positive. So I'm going to write like this. Start here. I'm going to go through this one, through that one, through this one, through that one, because I have to go through all of them. And there's my graph. Is that correct? I have no idea. I know it kind of looks like this. Okay? That's a darn good guess, but I don't know if it's exact. If you want to find out, graph it on Desmos and see how bad I drew it. Maybe I got it right on the dot. Maybe I'm way off. Okay? But that's not the point of this. The point is that you're sketching. Okay? A sketch means something way different than graph. When they say graph something, that means it better be good. When they say sketch, that means hopefully it's close.
Do you need to put like top left?
No, only on the other one they asked us for end behavior. Here, we kind of talked it out, right? We said, does it go both up or both down, right? Because it was a power of 4. But yeah, you don't have to list it if you don't want to. You actually don't even have to write any of this if you can just do it in your head. But I'm just kind of labeling some stuff. So let's look at 18 and 19. And that's it, right? So they tell us what our x-intercepts are. So, okay, great. -4. I'm going to put a dot right there. -1 and 5. So, okay, great. I don't have to solve for anything. They said it's a 4th degree polynomial. So that means it either both goes up or both goes down. Okay? We don't know yet. Okay? And they say the multiplicity 2 at 5, 0. So at 5, okay, at the point 5, 0, there's a multiplicity of 2. Okay? So let me see if I can figure out anything else about this. They don't tell us if the coefficient is negative or positive. So we're going to assume it's positive because I noticed in 19 they actually tell us it's negative. So I'm going to assume it's positive. So since it's a degree 4 and positive, it's up, up. Okay, so I'm going to start up. The only place where this has to bounce and go back is at 5. So that means I got to go through here, bounce, and there you go. There's that graph. Remember, it bounces at 5 because it has multiplicity 2. Even multiplicity means you bounce. Okay? If it's an odd multiplicity, you go through. Last one. 2 imaginary roots. That means there has to be a loop that either goes down and up or up and down, a change in direction that does not touch the x-axis. There has to be something like that, okay? That creates those imaginary roots. But they do tell us that it does have one intercept at -3, so I'll put that right there. It's a negative coefficient. Okay, it has 2 imaginary roots, 1 real, so my degree is 3, right? So degree of 3, it has a negative coefficient. So if it's an odd degree and it's negative, that means you start top left and you go bottom right. Okay? So, all right. This is what I would do if I were you guys. Okay, I'd start top left. It has to go through here. It has to come back up, but it cannot touch the x-axis, because by doing that, this piece right here, this creates the imaginary answers. That little up and down hill, that loop that looks like, oh man, this was supposed to reach all the way up to the intercept, but it didn't. It kind of came back down. So that means that there must be solutions right there, but they're not real. They're imaginary. Notice I don't know what the imaginary roots are, so I can't label them, but that's what's going to happen. So guys, do me a favor. Obviously, you have no homework because we just went over it. But